Hello students, welcome to Edusel. This video is all about DFS, which is depth first search. Those who directly watch this video without having any prior knowledge about the graph, why we are doing DFS and BFS, kindly watch the previous videos. This DFS is like which we are doing, but it is similar, like to search the nodes present inside the graph we are using it. Sometimes we can say is for traversing we need two algorithms. One is BFS, another is DFS. BFS stands for breadth first search, DFS stands for depth first search. Depth wise we can reach to the goal, or you can say while searching first of all we have to visit while before why we need it. As I told you as I told you in the previous videos, the searching or traversing are needed to find the shortest path. Why shortest path is important for us? Again, I'll tell you, the shortest path is important for us is to optimally use of the time and space. Okay? If you avoid the space for a timing, not an issue. To optimize the space, which is exactly meeting with the aim of the algorithm. That I told you, algorithm is used to effectively manage the artificial resources. Here, the artificial resources are two. One is time and space. As per the algorithm, algorithm is using to effectively managing the artificial resources. So here, the main theme of use the graph is, let us think the example of map. We are using map that though it's unknown place for us, but we want the effective utilization of that map is to find the shortest path. Why? Because we are indirectly managing our petrol as well as the time also. The shortest path will help us consuming less time as well as consuming less petrol. That is why, or less fuel you can say, might be petrol or diesel, or might be if you are using EV also, less battery. Like basically we need less fuel to reach to that destination. Okay, that is why we need the map. And map, I told you, it's a implementation of graph, because a cycle could be possible, like where you start might be that location will be your end of location, so you can start from the source and again you can reach. So definitely a cycle could be formed. That's why graph is getting used. So before that you should know where the location is exactly situated. So to find it, you have a random move in real life. Might be in that direction. Direction is added, no? So you are going to depth wise. If randomly you are moving, if which place is nearer to your place, you are moving right in that way, in random way, is a kind of you can say usefulness of BFS, because either you can start from one direction like left directions or right direction, or else you can start from left then right then left then right, or right left any direction. If you're without any correct direction, if you are just reaching the nearest cities to your city without thinking any direction, you can say BFS could be helpful. Means indirect use of the data structure named Q. Okay, Q data structure is used in BFS, breadth first search, and stack we are using in DFS. Why stack? The reason we will discuss, because last in first out operation is there, which is a part of breaking through backtrack things. Okay, we will discuss that one. Don't worry. So let us start with the algorithm. I kept it from Corman. As I told you, always I'm following the book, because any content you can get it from anywhere, but the correct content will be in the book because it's widely accepted. All the fellows who are reading also that are actually for those fellows are following the Corman book. Also, I should have to follow, because if I'll follow the Corman book, if you are watching my video, definitely you'll understand what is there in the Corman. At least you should say the correct thing rather than any anonymous thing. Okay. So DFS, they started with the algorithm, and G stands for the graph that we discussed in the previous videos. Here U stands for the vertex, which belongs to G dot capital B, means all the vertices. Like here the example for this A, this example I have already you can say I have cited from the Corman again. okay, with the algorithm is written one side and the example is written another side. We will first understand what book says. After that, I'll tell you my approach. After that, we will write a note. This is how the video is all about. Okay. So first, we will collect all the vertices like u, v, w, x, y, z. Why I'm saying that all the vertices, because G stands for the graph, the same graph name. uh, Capital B stands for all the vertices. As for the book, it has written. So it will be for all the vertices. What we have to write first, we have to change the color as white. Okay. If you are new for this video, kindly watch the BFS video, breadth for search. Then only you can understand why we need color. Okay. Next is pi. Pi stands for the predecessors, the previous node which we selected, because we are actually focusing on all the nodes first. So that time we are saying it is nil. Time here is time why you need it, because in a single direction if you are reaching, okay, somehow you have visited the node and you need to go back, okay, or you think no other places including this place are not yet visited, means all are visited. Suppose if all are visited, in that case you can be saying some time could be added as a variable. Like how do you say like you have visited for one time, or you have visited for three times, four times, eight times? For that reason we are just keeping time variable which is set to be 0. Okay. Next, the vertex u is there for each. Again, what we have to do is like all vertices, again we have to keep where if condition we have written. If that u color equal to white, then what we have to do, we have to run the widget function, DFS widget function, where we'll keep the graph as well as the source will start as u. Okay, here we are putting the source one. Here the u which is the previously declared is not that one. Here u we are saying we started with the u here. Okay, you can start from v, not an issue, but as for the program it is written as u, which is the source vertex for us. Instead of u you can write the source vertex. Now the DFS visit function, how it is calling, we will discuss. As we discussed, similar with the breadth for search, that could be very helpful. If you are new, you can watch that one. So time, you will first increase the time to time plus one, because the main reason is we are exploring. Exploring means we are visiting it. Once we started the visiting, instead of 0, if you want to start with 0, not an issue, not no need to update that. If you want to change it, like we need to change, why? Because we visited for the first time. You can say 0 means it means sometimes it means we have not yet started or not yet visited. So for that timing we just add 1 to it. As we have added, we set the distance. I told you within that the distance we are keeping. Distance indirectly says like how many times or what the weight it has. So like this. Okay. Next we change the color to gray. Why? The changing of color means we somehow started the work on it. That's why we changed the color. Okay. Next we started the for loop where we said s- small v which belongs to the adjacent of u, means the predecessors. We here we are keeping like which are next related vertices will be selected first. It's a part of exploration of that uh, edges, or you can say exploration of the vertices. Edges means u to v it has there. U to v means it's a next to u is u to v, or might be u to x. Okay, so it's basically source to destination we have to focus on, like what are the uh, nearest or connected or directed connected vertices which are next to the vertex which we select as the source vertex. There we keep a small v. Then we will check whether if that color is white or not, means we have not yet visited. If not yet visited, previously we said all are white, okay, and we set the gray like we started the work, and here we have to check if it was gray. Na, we will not check that one, because white means it is not yet visited. That's why we are going to visit it. Okay. Next, if we select that one, if this condition follows, next we say the predecessors of v, like the previous one which we select, suppose be the next vertex. Suppose we select. So here the small v is not representing this one, so it represents the adjacent of u. Here you can say the source vertex, but here as for it's quite confusing for the newcomers. I understand, but you here always been thinking whenever we say it's u to v, sometimes it has been written like u is the source and v is the next to you, which is two connected vertices with a direction. Sometimes we can write it. So here also the same naming convention, but think for a while like we started from u, which is a source vertex. Here the source vertex we kept as u. Okay, so then we visit whichever the uh, adjacent u we selected, like which are the nearer or the directed nearer, we will keep that one, but always in a one direction. Like in a BFS we are keeping all the vertices which are connected, but here we are not keeping all the vertices, only one direction, either left or right, or might be straight or might be down, like this. At least we have to follow one direction at a single stretch. Okay, next is once we select that one, then we will use the DFS widget with V, the new node which you have selected. The previous node will be set as black. Why? Because we thought for loop run for like what are the nodes that we selected, for loop run well, and we have changed the time and everything is changed as per this rule. Next, after the for loop, we set which was selected before, we will set that black, means we stopped it, like we said we have completed it. Okay, once we said we have completed, after that the time will be added again at the behind, or like here as per the example we will discuss that one. A slash will be there, after that we will write the time, whichever the time that u has previously will be updated. Okay, next the uf means this is dot f is finishing time of it, as dot d is the distance, dot color is we are changing the inside color of it. Here is the time we are using the finishing time, like we started uh, then we switch to this approach. Okay, as we started here, from the example you will definitely get it. You we started as with the example, uh, though there are two connected, one is v, another is x, you can go in any direction. Okay, not an issue. But as for the book, in second part, it has selected the uv, okay, which is the nearer part of the u. Might be you can select x, not an issue, but uh, they have selected u to v. Next, once V is selected, from V, we start exploring which one is the next to be selected. Like there is no other way except this Y. So Y, then we select Y here in C. Okay, A, B, and C. We have connected with this. Then we restart Y. There is no direct connections to anywhere except this X. So we reached X. Okay, once we reached X, here up to this we have completed for this D. Next, what we'll be doing, next we have to check. Okay, here up to this, up to E, everything is fine. So when it will be checking of if condition, whether is there any other node which is not yet visited, means is there any one which is connected through X. Now we are at X and we will check, is there anyone which is connected with X is not yet visited? No. So how do you get to know? If condition through if condition, here a connection was there, but we can find here it is dot dot dot, means we know it. When we do that, it is already gray, means it is visited. So no need to change it. We have already visited. Okay. So though we have already visited, so we set that one as dot dot, means we checked that one. Okay, somehow we have checked that. But no need to change because its color is gray now. If color is gray, means we have somehow visited it. Now for loop ends with that. Next, the 8 will start at F. F, from F, 8 will start. The color we set as black. Now this is U, and we set this as black, and we set the finishing time. The finishing time here was before 4, 4 plus 1, which is 5. Okay, so this is how we have updated this value with the finishing time. Next finishing time will be how we will be reaching, that will be changed one by one. This is what a backtracking we are doing. Like we stopped here for a while, then we are going for the backtracking of it. like your backtracking. Once we backtracking means we are going back and back towards the source only, and this is possible because of the stack. I'll tell you the new example. As for the book, I'm just running it now. Okay, once it is done, then we got this value because of this v. Here we found it and we set this as the color as this. Clear? Now, uh, due to v, what exactly we have to check? We have to check, is there any other connections? No, no such connections could be possible. So then what we have to do is we have to reach to the U, and through U we have to check, is there any other connections could be possible. Yes, of course, but this is black now. So though we started, we have checked it. So we just went for a while. Okay. Then we say it is black means we have set the thing well. Okay. Next we said everything is fine. Now there are other, as per this graph, some are not also being visited. Those who are visited, we said these are black. So here we can check for others. At 5 we have checked others. If white, then you start the DFS. Here it was, before that it was white. Now we change the color as that one, and the time which was 8, the time will be added as 8 plus 1, which is 9. So here it is 9. Next will be 10. Okay, once it is 9, then we have to check the exploration. You can check this one, you can check this one. There are two operations. Here it has already been, if you select this one, it has already been explored. So no need to change it. So here you can see the dot here. Okay, the dot is there where it has written like C. Okay, they named it. No need to name. If you want to name it, you can go for it. As for them, they have named it. And another option is there, which was white from this W could be possible. This is adjacent again. So they have selected this one. Out, if they have selected, the time will be added as plus 1. The previous time was 9. It will be added as 10. Next, what will be happening, like it will be checking, is there any other connections could be possible. To check that, we have to check the directions. Here is a self loop, which is a pseudo graph could be possible. So pseudo graph could be possible, so have to check. So it's already being explored, so no need to change the timing. Better we can make it dot. Okay, so once we make it dot, they named this as B. Next we have to check no exploration could be done. Then we go to backtrack. We have to select the backtrack. Once we have selected the backtrack, we kept the color, or we will change the color as black. Next what we are doing, we have backtracked it well. Now we switch to the W. So in this way, what exactly the DFS will be. DFS, they started from U, so you can write U, V, then Y, then X, though we complete it in this way. Next we started with the W, then Z. You may ask me, how could it be possible? I'll tell you the same thing. Like I'll tell another example, which will give you the proper idea, like how the stack is getting used. Only one stack with a processor. Like sometimes I have seen like processing. This is just an array. You think, okay? So I'll give you the example. The same example will run over here. It will work definitely. Okay. Example one I'm writing. Suppose any graph. Here you think A is connected to B, then C. Small example could be better for us to understand it. Okay. Suppose I'm changing it. D, then E. Okay. So here I changed it. Okay. As for this, if you want to find a DFS, keep stack DFS. Okay. What is the DFS? If you start DFS from A, always remember, DFS could be many. Okay. Like BFS, breadth for search could be many. DFS could be many. Many means you cannot say it's infinity. Infinite number of DFS could be possible. No, we are just changing the places. Then only could be probability. In place of 2 might be 4 could be possible. Infinite number of DFS could not be possible. I'm not saying that one. It could be possible with a finite number of steps, always. If it could be infinite, no? As for the property of algorithm, you can say it's not an algorithm because you cannot stop. No? If you cannot stop, so how could you say that you have certain time range? Clear, no? So if you started from A, there are two possible ways. If you start from C, so DFS could be different. If you start from B, the DFS could be different. That is why I'm saying many DFS could be possible. Okay. Now go for the solution. As for this, I'm just keeping one stack. Stack why we are using. We will read that one now. Okay. Though we start here, you can say the result or DFS also you can write in array format. I'm writing. Okay. In array format, I'm keeping the answers. In array format or in a bracket, you can use, not an issue. Okay. 1, 2, 3, 4, 5. Here I kept 5 indices. Just an array I've used to keep the thing. Okay, because one index, one value if I put here, it will take big of one n number of indices. Here also we'll keep it, but n is a variable. We may say 5 could be possible or 6 could be possible. In that case, it's somehow concept we go 5 a, we'll say, instead of n. Okay, so here if we start from a, now I have to write a there. Okay, also the same thing I have to write a. Why? Because we started from a. Clear? Though we started from a, there are two options. Either from B you can go to D, or you can from C you can go somewhere. Okay, so I started with A and I am going towards B now. This is a direction I did. Okay, once I am writing there, here also the same thing I have to write. Okay, here it explode. Now I think I should change the color. uh, Here that could be better to highlight. Once we have done with it, so we should change now. Okay, I explode. uh, it's not yet explode. It will be check now. Okay, it's done. Just wait. uh, we'll do that at the end. Now we are at B. Now we have to check whether is there any connections to B directly where we can move. Yes, there is an option to D directly. Okay, now here also you need to write D. Okay, then from D we cannot reach to E or we cannot reach to C. Then what do we do? Though we cannot reach to E and C, so in that case we will do one thing. We will go to the source again through which we can reach to C and D. Okay, for that reason we are doing the backtrack. Here, as per this example which we are doing, here the backtrack is all about to reach to source. Again from source, we didn't find to reach from W to Z. That is why I kept this example. Okay, so here the connection is being established through which we can reach. Now we can remove the, like, last in could be first out. Once it is done, like we are right now at D. Okay, so we are at D, B right now. Once D is getting popped out, so here we are right now at B. In this B, we have to check to backtrack it. We need to pop it out. We popped out it. Okay, once you're popping out, we have to go back to original source as here. From A, we have to check whether any other exploration could be possible or not. Here we have seen C is a possible way. That's why we are using stack. Okay, that's why we are using stack. Now from A, C could be possible. That's why you can write C there. Then we are at C, or no need to explore more on it. Though we are backtracking it, so during the backtracking, you can say it's better to say we have completed it. Though we are backtracking the thing, we can say we have completed it. Okay, because no other connections could be possible, that's why we backtracked. Here at A we are having the options to reach or to go back. That's why we have not yet been colored it well. Okay, so here in C you have to write C. Next from C there is another option is E. Okay, as you have written there, you also write that one. Is there any other connections could be possible or not? Yes, of course, D is connected, but it's already explored. No need to use that one. Better you can go back to check whether is there any corrections possible or not. To go back, you have to remove your and color it. Now we are at E. We remove that E now. Now we are at C. Then we didn't find any exploration from this. Then we go back to A. Again here A. No need to explore because no such values are there. Clear? So now it's explored well. We can say in a single direction we are moving from one into another end, through which we can reach our destination. This is one possible DFS. Another DFS could be possible is, I'm just writing it, A, B, C, D and E. Here, 5 indices I kept, which is an array again. You can say this is an array. Clear? So, if you start from A to C, you can C, then E, then D. But after that, you can backtrack. So, I'm just writing that one, A, C, E, then D. I need to backtrack. Once I'm needing to backtrack, then I switch to A again. Okay, like A, C, E, D, then I need to backtrack, means I need to remove one by one to check. Then from A there is a possibility you can write B. So there are two DFS could be possible if you start from A. This is why I'm saying DFS could be many, means this could be more than one. Okay, but not infinity, not infinite. Okay. So in this way we can find the DFS, but as per the note, if you can write the note, as per the note, DFS should follow a direction, okay, and stack data structure is used in DFS. Why? For backtracking, stack data structure is useful for backtracking. Okay, for backtracking we are using it, and stack data structure is used in recursion. Okay, or function call, you can say, or function call. So in function call we are using stack, and the time complexity of DFS is big of V plus E or N plus E, or you can say V plus E or N plus E is for adjacency list. If you are using adjacency list, how and why, that you may go to the introductory video of graph. If you are saying V square, you should say it's adjacency matrix. How we are getting it, you can check the introduction video too. And also, if you can say the space complexity is V square due to adjacency matrix is also correct. Why? Because it is there, we have discussed about this adjacency list and matrix in introductory video of the graph. Here I can say the data structure stack is helpful for DFS, backtracking, recursion. So almost 50% or 70% of the problem is solved by the stack. So I must say stack is the king of all the data structures. You can say. No doubt all data structures has its own importance. Like linked list also helping you to reach any data directly. That could be helpful. Like you can say if you can have a proper index, like if you have hash, you can reach to any particular location within big of one. Like with the one index, like with a constant time, you can reach any particular location using hash. And you can say like many data structures could be possible. Many data structures are, they're having their own you know approach to solve a problem. They have advantages, disadvantages too. Like array, you can say the basic of data structure, you can say is array. But for me, stack is helping all kind of problem like which are to be solved as an immediate, you can say. Or like stack is also helpful for topological sorting, like in a sort stack we are using. So I have not written it because in the next video we are going to read about the like topological sorting. There I'll tell you stack is also helpful in that case. So almost all problems is getting solved by the stack. That's why I'm saying stack is king of all the data structures. So thank you, thank you for viewing this video. I hope it's clear for you. If any doubt, you can ask me through the chat box, comment box below. Thank you. Have a good day.